So, good morning. Uh, Thank you for coming, and also thank you for inviting me for this talk. The talk is Next Generation Large Telescopes. To me, it looks like you are already familiar with telescopes, right? Yesterday already you have a couple of talks. So I'm also going to talk about telescopes, but large telescopes, okay? But there's also going to be some repetition, right? And repetition is good because it helps you understand things better, right? So one more thing, I have made this talk to make it more interactive, which means I'm going to ask question and you have to raise your hand. Don't start speaking in between. You can answer. Okay, if there is more than one person, I have to just pick you up and answer. So that's how we are going to learn about large telescopes. All right. And okay, so before we start talking about telescopes, let us talk about our eye. Eye itself is some kind of telescopes. We'll see how it is. But the question I want to put you is how far we can see with naked eye, right? Who wants to take this question? How far can we see with naked eye? What is the closest you can see? Clearly, like you can read your notebook, right? How far is that? Just maybe 10 centimeter or 15 centimeters, right? That's the nearest. But how far you can go? Hmm? Huh? Yeah, please. Huh? No. See, you are able to see me. I'm more than 1 meter. Yes? 200 meter. Why? If you go out, you can see some of the buildings which are miles away. So it can't be 200 meter either. Yes?
Sir, my guess is maybe 8 kilometers. If you're standing on a height, we can see like this.
8 kilometers. Okay. Yes?
Thousands of kilometers.
Thousands of kilometers. How do you know that?
We can see Jupiter.
Oh, he says we can see thousands of kilometers because we can see Jupiter. See, this is how you should think. Jupiter is thousands of kilometers. Your eye is able to see it. Very good. Same answer, right? Now, if you have something different, you can tell me. Okay? And what more?
On the Jupiter, we can see stars too.
We can see stars. Stars are farther away than Jupiter, right? So that's very nice. So I can see from few centimeters clearly. You can read your notebook. You can see mountains. You can see aeroplane flying tens of kilometers, right? You can see moon, which is the closest celestial body. You can see planets, which are farther away. You can see stars. And if you happen to be in a place where sky is very clear, you could also vaguely see the Andromeda galaxy, which is the closest galaxy to Milky Way, right? So, so coming to the original question, how far you could see? What does it depend on?
Cloudless sky.
Well, of course, it depends on cloudless sky, yes.
How far light can reach?
How far light can reach? Light could reach to the farthest corner of the universe, right? But what would it depend on? Yes.
And sir, so for if we are looking at an object, it depends. If the object is a luminous body, then it depends on the luminosity of the object.
Yes, very
If it
nice.
is a non-luminous
Right.
body,
So
it
first
depends
thing
on
is there is a air in this room. Can you see those air molecules? Why? Two reasons. They're too tiny and they don't have light. Right? So, but you can see all these things. Right? If the room is completely dark, even the bigger things you can't see. Because so you need what? Two things. The object should be big enough and it should also be bright enough to be seen. So no matter where it is. So distance wouldn't matter as long as you have a big object and as long as it is bright enough for it to emit light and the light to reach our eyes. Okay, so that's what makes, so size and brightness of the object will decide how far we can see them. Okay, Is that convincing or not? Okay, so that's good. So that is about eye seeing the things. But since you are interested in building telescopes, you are also interested in studying what is there in the universe, right? So the first question is, how do we study our universe? What's the way to study the universe? Like, yes?
So from Earth, if we do not have telescopes or any other such device, we can map the sky by our eyes, just like our ancestors. If we have technology, we can use ground-based telescopes.
Right, but what you are looking at when you are looking in the sky?
We look at stars, moon.
So what is their star? Are you feeling them? Can you touch the stars? Right, then what is it that you are observing? Light. Okay. So there are a couple of ways to study the objects in the universe, and light is one of those. Okay, so the method that we study the universe is through the light that comes from these celestial objects. Okay, so that light, technically we call those as electromagnetic waves. So the 99% of the information that we have about the universe reaches us through the light. There is also high energy cosmic rays. Those are like particles, neutrinos, gravitational waves you may have heard. And also sometime there are space missions sent outside to collect samples and bring it to us. So all these all these things are ways to understand the universe. But remember, majority of our knowledge, most of our knowledge about the universe has come through the light. We just observe those things. So light is important. All right. So this is electromagnetic spectrum. I wouldn't go into details. See, what we are seeing with eyes is only a part of that continuum, right? This big wire that you call, but the electromagnetic waves can lie on the longer side where you have radio waves, and the shorter size where you can go up to gamma rays. So somebody may have talked to you about multi-wavelength astronomy. Okay, so multi-wavelength astronomy means covering all the electromagnetic spectrum, because celestial objects emit light over the entire electromagnetic spectrum. Okay, but in today's talk, we will be focusing only in the visible light. Is that all right? Okay, so then the question is, now can we see all stars and planets with our eyes? Why and why not? Yes.
We can't see all the stars and planets with our eyes because they might be too far and they
Yeah.
might reflect or emit less light. And
Correct.
sometimes, even if it's visible normally, the clouds stay there.
Very nice. So I think that's a good answer. Everybody understood, right? There are more stars than our eye can see. We can't see those because either they are too faint or they are too distant. All right, very nice. Okay, so then that's where you need telescopes. So, okay, the question is what are the telescopes and why do we need them? So he has already answered that there are objects in the universe which are fainter, which our eyes cannot detect. But as a scientist, you need to study them. So the way to study them is to use telescopes. All right? So then the question is, what is telescope? Yes?
It is a device which helps us see.
So let us call telescope as a scientific instrument. It's a device, yes, good.
It is a scientific instrument which helps us see celestial bodies through lenses.
Yeah, so she's saying it's a tool which scientists build to see celestial bodies, right? But how does it work? So telescope has three very important properties which you have already studied. One of them is that telescope is like a bucket, right? When you put a bucket outside, if it's raining, what's going to happen? Water is going to be collected in the in the bucket. If you have a bigger bucket, you will collect more water. If you have a smaller bucket, you will collect less water. So telescope is something like that. If you have a bigger telescope, it will be able to collect light over the large area. Okay, which means what? You can see the fainter objects, right? Fainter objects will have very less light. But if you can collect it over large area, you would be able to see that. So one important property of the telescope is the collecting area of the telescope, how big it is. That's very important. Then another advantage of telescopes is that it makes things look bigger. You're going to build a telescope and you will see that you can produce a magnification in the telescope. You can make things look bigger. All right? And very important one is that it gives you a better resolution. So resolution of the telescope is its ability to resolve small details in the object, right? When you look at a tree from here, what is tree consist of? Huh? There are leaves, there are branches of different sizes. Huh? There's a trunk which is big. So trunk you will be able to see from any distance, from a larger distance. But what about leaves? So what is happening? Close by trees, you can see the leaves clearly. But if you're looking at the tree from a distance, you can see that is a tree, but you wouldn't be able to see the leaves separately. So that's what is the resolution. Resolution means the ability of the eye, or in this case, ability of the telescope to see the details in the object. So if there are finer details, you should be able to see them. Okay, so that's fine. Now telescopes come in different flavor. There are radio telescopes, there are optical telescopes, and so on. Space telescopes, that also you must be aware. Okay, then, so before even, now we say the telescope collects light, but what is it that, what is the crucial thing in the telescope that help you collect the light? The most important thing in the telescope. So, okay, so there is something called lens, just like smartphone. So how does smartphone work? Can you tell me? So with smartphone you can take amazing pictures with the modern smartphones. So what is there in the smartphone? The most elementary thing that help you capture the images, yes?
There's a sensor that collects light through pixels.
Sensor doesn't collect light. Sensor records the light.
Yeah, it records the light that comes back and turns it into pixels.
So what is that? What is the component which collects the light? In your mobile, there is a lens. So if you are curious enough, you can see these things, right? This would be the lens, and if some of your smartphone has gone bad, you can try breaking it. You'll see small lenses, right? So these lenses are complicated set of lenses, not just one lenses, because you want the image quality to be very good. So you can't do it with the one lens. You will learn these things, why you need more than one lens. But the main thing is the lens. The lens which captures the scene from outside, forms that image on the sensor that is set. Sensor just records it, just like a photographic plate. All right? But if I put a photographic plate here, will it be able to take your image? You all are sitting here. I don't see your image on the screen. Why? Light is coming all the way, but I don't see the image. Yes? You are illuminated, very well illuminated. But if I take a camera, I will be able to take. Yes?
Because its field of view is less, so it can't capture all.
Okay, let us say only you. If I am only considering you, your field of view will be smaller. So why would it not come? Yes?
Well, I guess we need something which could take the light.
So even though all of you are sitting in this room, there is a light which is coming from these light sources, tube lights and so on, hitting you and getting scattered from your face and everything. But image is not formed. It's going in all possible directions. I am able to see you. Your image is able to form on my retina. How is that? Because I'm collecting the photon. My eye is like a, yes? There is no lens here, right? If I had a big lens, then I would be able to form the entire image and project it on the screen. right? The fact that I'm able to see you, that same thing is happening. Our eyes are doing that. It's collecting the light. The image is formed on the retina. It's a simple lens. Our eye is a very simple lens, biological tissue, but fabulous because, well, in later classes you will learn how the eye has evolved and how it has become such a wonderful organ of human body, which helps us to survive. Okay, but it's just simple, transparent, flexible membrane which help the image to form on retina. Image is inverted on the retina, but our brain interprets it and gives us the right. Yes.
The lens is called cornea.
I'm sorry.
The lens is called cornea.
The lens is called cornea. Yes. Pupil. That's not cornea. Cornea is the entire thing. But the small thing, small circle in the middle of the eye that you see is basically that lens which collects the light. Any questions so far? Right, so you need lens to form images, but how does lens form image? That we will understand. So lens in the camera helps us to take the images. So image has to form first. Okay, so now let us understand how the telescope does that, how the image is formed, because telescope can be lens or it can be mirror, that we will see quickly. Now there are two very, very important but simple laws on which lens works. One is called the law of reflection and another one is law of refraction. You may have heard about it already, but I will just simplify. So let us say this is your lens, simple convex lens, biconvex lens. So what does this, the property of this lens is that whatever rays that are coming from, let us say, far away distance, we represent those rays as a parallel rays which hit the lens, and the lens has this property of bending the light through the law of refraction. Now, one set of ray which is shown here is coming from, let us say, a star which is at infinity, and the shape of this lens is such that these rays are bent continuously onto this single point. The rays which are on the periphery, they are bent more, whereas the ray which is going through the center doesn't bend. This is all the law of refraction is in case of lens. All right. Now, if I had another set of ray coming at an angle, that would have been formed somewhere here. Now, while making telescopes, let us say if this surface is not properly shaped, what would happen? Then all the rays, such rays will not hit single point. And if they don't hit single point, what would happen? Distortion, right? You will not get a sharp or clear image. Remember, so that's all it takes. Okay, so if let us say you have a lens here, there's another scenario, and this is a tree somewhere far away from its twice the focal length, then it's going to form an image, something like this, inverted image. So all we have to do is put a camera here, sensor here, and record that, and that will be image. Is that clear? Okay, so this is another small simulation showing how a light coming from a distant star gets focused to one point. Now, what lens can do, same thing can be achieved by a mirror. So here we have a curved mirror, also called concave mirror. Shape is like this. So the inner part of the mirror is the reflecting portion. Okay, and again, let us say the light rays start from this top of the candle you're considering, one of the rays, and one ray you go straight, another ray. See, this point is emitting ray in all direction. All we are doing is just considering two rays in order to understand where and how the image is formed. So one ray goes straight. So the law of reflection would make it, if there is a ray which is parallel to the optic axis, after reflection it should go through the focal point. Right? This you will learn why it happens. And if there is a ray which is going through focal point, after the reflection, it will go parallel to the optical axis. Okay? And that's all it takes. So place where these two rays would meet, that's where the image of this point is formed here. So if you have a full candle, you'll get a image of the candle which is inverted if it was placed somewhere at this point beyond C. C is twice the focal length. All right. So your telescope, if they are refracting telescope, they work on this principle. If they are mirror-based telescopes, they work on this principle. Any doubt here? No? Very nice. Okay, so one more thing I want to say is that the lens-based telescope has some issues. The one issue is that light that lens bends, light has 7 colors, right? The visible light that we are talking, even though full electromagnetism have everything, but visible light has 7 colors, and the property of the lens is, the refractive property of the lens is that each color is bent different way. The red color is bent slightly less, the blue part of the color is bent more. So you don't get a sharp image. See, ideally to get a sharp image, as I said, all the rays should converge to single point. That is the focal point. But since light has several colors, all the rays wouldn't converge to single point. So your image is going to be slightly blurred or colored. Okay. So there are ways to overcome this drawback of the lens. One can use doublet, which compensate this differential bending to get single point. But lens-based telescope also has some another drawback. If you want to go for a bigger telescope, then lenses are not most appropriate elements. Bigger telescopes are always made from mirrors, right? Reflecting mirrors. So this, whatever I have described, is called chromatic aberration, and lens suffer from chromatic aberrations, but the mirrors don't. No matter what is the color of the light, it will just always be focused at one point if there is a parallel set of rays. So there is no chromatic aberration in the mirrors. The second practical consideration is weight and size of the lens, right? Lens is a big, bulky thing. So if you want to make 1 or 2 meter class telescope, making such a big lens itself is technologically it is challenging. Plus holding it, right? So the weight will become more. So your structure which support the lens itself will not be able to hold it steadily. Okay, so that's another thing. And plus light is going through the material, right? So if there is a inhomogeneity within the material itself, it will cause some error in your image, right? So that is for, if you want to make a telescope with the lens, the glass material has to be extremely homogeneous, pure, right? When you grow the glass, there shouldn't be any bubble inside it or any impurity, otherwise the image will not be sharp or clear. Plus, as I said, when the telescope size becomes bigger, the lenses become more bulkier, heavier, and it becomes difficult to support them, right? Whereas mirrors are easier to support. So structure of the telescope is also very important. Okay, so I wouldn't spend too much time. You will already probably know what are different configurations of the telescopes. Like this is prime focus, Newtonian, depending on where you want to put your camera or where you want to put your eyes, right? You can have different flavors or different variations of the telescopes. So again, I'll not spend time on this because somebody has already talked about it. So let us see, there are some important questions. Now, yes?
Actually, that part was not done.
Oh, this part?
The previous part.
This one is not done.
done.
Okay, great. So let me just tell you, as I said, telescope, so once the telescope was discovered, you can tweak it to any configurations, meaning you can make different variant of the telescopes. So these are different variants. In this case, you have a primary mirror, which is again a concave or parabolic mirror, and you have these light shown by these parallel arrows coming from a source star which is at infinity, and this mirror would focus it somewhere here. So this is called prime focus telescopes. Okay. What Newton did was, because now if you make such a telescope and you want to look at stars with that, how would you see? That's not possible, because your eye should be here to see the object, isn't it? But if you put your eye, you will block the light, right? You can put a small sensor if it is possible, because sensor is smaller than this whole size. That is possible. But if you want to look, then that will become difficult. It will block most of the light. So prime configuration is not suitable for looking the stars with this kind of telescope. What Newton did was he put a flat mirror somewhere in between to again redirect the light out of the telescope tube. That became Newtonian configuration. So here now the focus is the light is focused at this point, and you can easily put eyepiece and look at the stars. So the telescope that you will be familiar or somebody will show here would also be probably Newtonian if it is a reflecting telescope. Okay. Then most of the scientific telescopes, the bigger ones where you do research, they have slightly different configuration because you want to attach instrument, and instruments are usually heavy, right? Telescope is only collecting light. It's not doing anything. It's not telling you anything about the light. All its capability is just keep collecting light and give you. Now what you do with that light, what property of the star you want to infer by studying the light. For that you have to put instruments, right? For example, if you put a camera, it will become an imager. It will take images, right? If you put a spectrograph, it will disperse the light and tell you how much light is going into the blue region, how much is going to the red region, and in between. So that will tell us that will tell us about the stars and the chemical composition of the stars, because it's not going to be just spread of light. There's going to be some light missing in between, and that light is absorbed by some atoms and molecules in the atmosphere of the star. So essentially, by looking at the star using a spectrograph, you can tell what chemical elements are present on the surface of the star. That's remarkable, right? That's remarkable. You didn't hear. You were, yeah. So we'll come to that little later. But the point is, if you want to attach an instrument to the telescope, somehow you have to collect the light and bring it to the back side of the mirror. So bigger telescope has a hole in the center of the bigger mirror, right? And light, this is the light that is coming from star. There is a small mirror here, concave mirror. So light comes here, gets reflected again onto this surface, and then this mirror will focus it somewhere here. So this is called in Gregorian configuration for solar telescope, but these are all Cassegrain focus. Cassegrain focus means light is focused behind the primary mirror. Primary mirror is the main mirror of the telescope which collects the light. Okay, so there is another configuration of Cassegrain focus. There can be third configuration which is called coude. So you collect the light. This is a secondary mirror, and this is a flat mirror which again diverts, which throws the light or deflect the light out of the telescope tube. Something similar to this, but slightly different, right? Is that all right? This is how you manipulate. The idea is you should be able to steer the light out of the tube into your telescope instrument. And these configurations help us to achieve that. Any questions so far? Okay, great. Then I will ask some questions. Okay. So some important questions. Some of these questions I have already answered. What makes a telescope powerful compared to eye, for example? Okay. Does the size of the telescope matter, and why? So who wants to take these one after another? Yes, please. First one. What makes a telescope powerful? Meaning, why telescope is a better tool compared to human eye?
The lens makes the telescope more powerful
Mhm.
because it magnifies.
So lens or mirror? Now you can say it interchangeably. Okay.
Lens or mirror,
Hmm.
depending which telescope you're talking.
Yeah, if he says lens, understand there is also mirror. Okay, or vice versa. Yes.
It makes it more powerful because it magnifies whatever we're trying to identify, such as a star or a system.
Right.
We can see it with more detail.
So those three things I have already described. There are three properties of the lens or mirror which makes telescope powerful. One is it has a magnification power, right? The small things can be magnified. The image can be made bigger so that you can see the detail. Second thing is
Provides better.
the amount of light that a telescope collects is proportional to the area of the telescope. So bigger the mirror, more is the light you can collect. Okay, and third thing was the resolution. That's a tricky thing. Resolution and magnifications are not same. Magnification will just give you bigger thing. It will not tell you whether. Now if I magnify this image, I will still not see the hairs of the person, right? But if I had a better telescope which has taken this image with a bigger telescope, I would have resolved the hair structures also. Got it? I'll clarify that in a short while. And does the size of the telescope matter, and why? It matters for three things, because it's giving you, yes?
Because it can gather more light.
Yes.
And we can see farther.
Yes, if it can gather more light, that's fine. Things will be brighter.
And the fainter objects can be used.
Yes, because it has a capacity to collect more photons. So even for source which is faint, but which is at a faint or at a larger distance, you would be able to collect lights. So some of the source which I cannot see, telescope will be able to see. Very nice. And resolution. Okay. Do bigger telescopes see farther, clearer, or both? Yes.
Bigger telescopes have bigger mirrors so it can see more clearer.
Bigger telescope has what?
Like it has a comparatively bigger mirror.
Barrel. Oh, you mean tube? Mirror, yes. So all these questions are interrelated. I have just rephrased them in different things. Yes.
Mirror, so and then it can collect more because it has a bigger mirror. We can see clearer. We'll have a better resolution.
Yes.
And
So
it can collect more light.
yeah.
So
So
we can see farther.
correct. Because if source is very faint, you cannot see it, right? But if you can put big mirror, you can see it because it's collecting more photon. Plus, because mirror is bigger, clearer means resolution. Remember that. Resolution means ability to see the smaller details in the object. Okay, look at this. What is this? This is a curtain. Can somebody describe me the curtain? Sitting here. What is it?
Curtain is a large cloth
Yes.
which is used for decorational.
No. You just describe what you see there.
Okay, sir. So this is a curtain. It has a cream kind of color
Yes.
and it has lots of wrinkles.
Right.
And
Yes.
it is
So wrinkles, right? Folds. That your eye is able to see. Can you see the threads? Those are details. So you are seeing things at different resolution. You can see the folds but not the threads. But if you go closer, you should be able to see threads also, right? Okay, so bigger telescope can give you better resolve or clarity. That's the point. Okay, and if you could place a telescope anywhere, where would it be? So it's not enough you make a big telescope. It's also important to know where to put that telescope. I'm not talking about the telescope that you're going to assemble. I'm talking about the telescope which is used for research purpose. Somebody else? Yes.
like somewhere where the sky is clear and it's easy to see it.
Correct. Because big telescope costs so much money, you don't want to put it somewhere where it's cloudy all the time or the sky is bad. Bangalore has a bad sky or good sky? Why? Too much of light. Why? But why does it interfere? Light pollution. Why would it interfere?
Interfere with the light coming to the objects will be very visible.
Huh?
When there's too much light, the dimmer objects will be very visible.
Dimmer object will not be visible. So what is light pollution is adding as a it's a noise. Right, it's acting like a noise. Okay, so astronomical sources are faint and you definitely need darker skies to be able to see them. Okay, this I have already explained why we don't use lenses for the bigger telescope, because telescope have a chromatic aberration, they are difficult to support because they are bulky and heavy, whereas mirrors are easier to manage. And how do we avoid blurry images caused by Earth's atmosphere, caused by the turbulence in Earth's atmosphere? We'll come back to that little later. Now, since I talked about three properties of the telescope and I want to clarify what the resolution means, so I have taken one example to demonstrate that. So everybody has seen cars, right? Nighttime driving and so on. And typically the headlight of the cars are separated by 1 or 2 meters, depending on whether you have a small car or big car. All right. Now, if the car is closer within few tens of meters, your eye very clearly sees the headlight of the car, right? Two separate headlight. And if the car is further, let us say, a half kilometer, you would still be able to see two headlights of the car. Okay, but if the car is, let us say, more than 3 or 4 kilometers, your eyes is still detecting the light, but you are not seeing the headlights separate, right? So here, at this distance, you have a good resolution, but at this distance, your same eye is not able to resolve the two headlight of the cars, okay? So if your eye was bigger, then you would have easily, you could have easily resolved these. Here they all both got merged together because I can't see the details. Just like I gave you the example of a tree which is close by, you can see all the small branches, small leaves and so on, but if the tree is far away, you wouldn't be able to see. You can see the tree but not the details in that. Same thing is happening here. Now human eye, the pupil of human eye, which is a lens, is roughly 2 to 3 millimeter in diameter, okay? Now remember, I am talking again and again about the resolution, and resolution of any optical instrument or eye would depend on these two things. The wavelength of light that you are seeing, proportional. So this is angular resolution, meaning two objects, how close they have to be resolved. So that depends on the wavelength at which the light is coming from that object, and also the diameter of the telescope, okay? So when r is small means you can resolve the angular separation of the object which if it is small, right? So d is the diameter. So when you make d bigger, what will happen to r? R becomes, this is just something divided by a quantity. When dividing quantity is bigger, what happens? What happens to r? R becomes small, right? Which means you can resolve the small angular distances. It becomes better and better. So high D gives you better angular resolution. Okay, so remember that. So if we put everything together, human eye can resolve things, let us say, or to a typical distance of 3 kilometers, if we have to take car as an example. Okay, if I have a 1 meter class telescope, it would have resolved the headlight of the car at a distance of 1500 kilometer. Meaning what? 1500, what is 1500 kilometer from Bangalore? Big town. Pune? Maybe? Pune? So if the car was there in the Pune and if the headlights were bright enough, telescope would see just something like this, it will record it. 10 meter class telescope, 15,000 kilometer. If the car with lit headlights was in California or somewhere, your 10 meter class telescope would see them distinct. 30 meter telescope, 45,000 kilometers. So this is amazing, right? If you keep on increasing the size of the telescope aperture, your ability to resolve becomes better and better. And that is the reason why scientists make big telescopes. Because when you go farther and farther, the angular resolution becomes smaller. So telescope should have the ability to see those things separately. Okay? So collecting more light is definitely very important. Okay, having magnification sometime is important, not all the time. But resolution is one of the most important feature or characteristics of a telescope. Okay? So far, any question? Okay, now let us see here. These are the 3 images of the sun taken by different telescopes. This image is taken by a small telescope of, let us say, 5 to 10 centimeter. What do you see here? It's a plain, flat image, right? But that's not how sun is. When I take a bigger image, a bigger telescope and look at the same sun, I start seeing the details in the solar disk, all the small features that are there. Okay, and if I take further bigger telescope, I would see these granulation structures, even at sunspots, details of the sunspots. So this is the importance of resolution. Okay, same thing here. Telescope of the image of the Jupiter taken by 5 centimeter telescope. This is taken by 20 centimeter and this is taken by Hubble Space Telescope. So the magnification is all same. What differs is details. So that is the resolution. Here many more details are visible, which means 2.4 meter HST has a better spatial resolution compared to smaller telescopes. Okay, that's the reason why we make big telescope. Now when we make big telescope on the ground, there's another one important problem, bottleneck. Yes? Yeah.
Was our resolution?
I'm calling that as the angular resolution, yes.
Because
So lambda is a wavelength. If you decide to look at things in blue filter, then the smaller lambda, lower wavelengths will help. You want to make R as small as possible, it's the angular resolution, right? So smaller lambda and bigger d will give you better and better resolution. Okay, so bigger telescope. So what are the telescope doing? They are making the images sharper, more clarity, more resolution. So different words, but it means same thing. Resolution, clarity, sharpness, everything means same thing. Okay, just another thing. Now look, this is the effect of size and magnification. So again, Jupiter and its moon, images taken by different telescopes. Size of the telescope is different and magnification power is also different. So can you see what is different in 3? Magnification is higher as you go to the right, all right? But sharpness also increases. So when you are using big telescope and big magnification, you get to see the details and also be able to see bigger, see the everything bigger, magnified. And this is a star cluster. Taken, leftmost image is taken by a small telescope, whereas the rightmost image is taken by the bigger telescope. So what is the difference between these 3? Details definitely, but what other than that? There's no magnification. All I have same magnification here. Magnification is only coming here. Here nothing is becoming bigger, right? Resolution is better, but other than that,
In the third
image,
picture,
mhm,
there are
more stars.
And in the first one, the dim stars are not visible.
Very nice, right? So not just the resolution, but also ability to collect more light. The bigger telescope is able to pick up stars which are not seen here. Those are fainter stars, right? Because fainter stars have less light, you need bigger telescope, then only they will show up. So both resolution and light gathering power of the telescope improves as telescope becomes bigger. Very nice. Okay. Then now effect of location. As I said, you can't put a telescope in a noisy, in a place where there's too much of light. Okay. So the top image is basically telescope, same telescope at 3 different locations. This is somewhere sky is very dark. This is somewhere countryside, and this is in a city. So what's the difference?
The city one is much more lighter than
The leftmost has
clearly.
lot more clarity, which means what? So the pollution, light pollution that we are talking about, it's acting like a noise, right? So if there are fainter objects here, the noise itself is more brighter than those objects. So they won't show up in this, correct? So the importance of putting the telescope at darker location is also key thing when you're building big telescopes, right? So this has a clear all the objects are seen clearly. Many more objects are seen. This is all coming because of the effect of noise. And here, same thing. It is here you can see a galaxy with lot more details and also many more objects. So noise is affecting your resolution and it's also affecting your ability to see fainter objects. Resolution is clarity, correct? Because there are lot less objects here than here, right? So one has to be careful when you decide to make big telescope. Now, yes, you make big telescope, take it to the good dark sky locations, but you still have issues. Now, I want you to tell me what is happening here. What is this? Think, watch it carefully. Now you have to raise hand. You want to take? Yes. Yeah, but what exactly is happening? Yes, there's something ground heating. Yes. Not you. Uh-huh. He says it is because of the water vapor. Picture is warm. Yes. Huh? What is humidity? Lot of water in the air. Okay. You want to tell?
Sir, so like example, if we put fire
Uh-huh.
and we want to see through the fire,
Yes.
and it's gas is going up.
Yes.
So as we try
Okay.
to see
So
through
this
the
is
fire,
typically very nice. Sit down. I think most of you got it, but let me just explain it. So this is a typically a hot day in a city, right? On the road where people are walking. On the hot day, the ground gets heated very fast. And as a result, air which is closer to the ground also heats up. So when something is heated up, it becomes less dense, so it rises up, right? So you have heard about mirage, right? It's basically optical mirage. Okay. So now because of this hot air which is near the ground is rising up, it is mixing with the cold air and creating lot of turbulence. Okay, and camera which is taking these images, so the light rays from one objects are not reaching at unique point on the image plane. Okay, so as a result of that, you won't see a clear image. Now same thing can happen to the star. Heating is always there. Daytime, when sun is there, ground will be heated, the hot air will rise, it will mix with the cold air and create a turbulence. So large telescope usually suffer from this kind of phenomena. So if we were looking at the stars with the telescope, we might also encounter this problem. Okay. Now because of this, noise is affecting your resolution and clarity. This is even making it worse. Okay. So even if you make a big telescope, you will not be able to resolve things because of this mess. This is called turbulence. Turbulence induced by Earth's atmosphere. So then the question is there a way to counter it? If you make big telescope and if it is not giving you a good enough resolution which its diameter of that telescope can give, then there is no point. You can collect more photon, but no funding agency will give you money just for collecting more photons or magnifying things. You need clarity, you need resolution, and turbulence affect your resolution. So how do we compensate that? How do we eliminate the turbulence? Yes.
so we take telescopes out of Earth's atmosphere like Hubble.
Yeah, that becomes very, very expensive. And big, if you want to take a big telescope out of Earth's atmosphere, nobody will have so much money. Right? Clear sky can slightly reduce it, but it cannot altogether eliminate it. It would still impact. So let me just tell you, if you have a 20 centimeter telescope, which is not very big, right? Then you can get clarity which is proportional to its diameter. But if you make telescope bigger than, let us say 15 to 20, if you make 30 centimeter telescope, its resolution is still going to be like 15 centimeter or 20 centimeter telescope. If you make 1 meter, 10 meter, 20 meter, 50 meter, no matter what, the resolution is it's going to give you a resolution of 20 centimeter class telescope. That's bad, right? Okay, so there is a way, there is a technological way to overcome the effect of degrading effect of Earth's atmosphere, and that is done by, okay, so before I go, now that was image taken of people walking on the road. Now same, the image taken by a telescope in different seeing conditions. So seeing is a property which quantifies whether a site is good for observation or not. Now you can see the rightmost thing. Here the star image is like, if you have a telescope, you're taking the image, it's going to be dancing all over. It's splitting, dancing, and so on. Okay. Come to the leftmost point. Here you are exactly getting the point source. So which image is better here? The first one. So turbulence is minimal here and turbulence is maximum. So bad site will have this kind of property and good site will have this kind of property, right? But even at the good site also, you will see that you are not getting perfect resolution, right? So just to clarify once more, the effect of atmosphere, you can just see these three things. So this is for the stars and this is for the extended object like Jupiter. So here, when things are moving very fast, details are lost, resolution is compromised. In all these three cases, the telescope is same. Only thing is the atmosphere quality is varying. So in this case, turbulence is there, but it's not very severe. So some details are available or are visible. But in this case is something like this, right? There is a small turbulence, the overall image is moving, but the details are not lost. Correct? So one has to also consider which site you are putting the telescope. So site has to be good. It should not have too much of turbulence. So reason why most of the bigger telescopes, they are put at mountain heights. And why that is the case? So two things happen when you go up in, air is thinner. Yes, turbulence, the strength of the turbulence depends on the density of the air. But as you go up in the atmosphere, both density and temperature decrease. So that is one reason why bigger telescopes are put on sites where turbulence effects are minimal. Okay, now how much time I have? Can somebody tell me, please? Okay, so this is another example. Again, this is a real image taken by 8-meter class telescope without something called adaptive optics. So as I said, one way to sharpen the image from a bigger telescope is to use a technology called adaptive optics. Adaptive optics is a way to correct the aberrations or errors that are introduced in the beam path because of the turbulence. So here, stars are just like no details, or everything is lost, even though it's a big telescope. But when you put adaptive optics, you are able to see all these stars in much more details. Okay, so this is what. So nobody puts bigger telescope without adaptive optics because you should be able to take care of degradation in resolution that happens because of the turbulence in Earth's atmosphere. Okay, how it is done, I will tell you in the next few slides. Okay, so there is some other instrument which gets attached to the bigger telescope, which we call adaptive optics correction instrument. So that's how it works. So your telescope is there, light is coming from the star, it is entering Earth's atmosphere, which is turbulent. It is distorting the wavefront of the light, okay, which means it's no more flat. All the parallel ray which I was drawing, they will not be parallel anymore, they would be scrambled because of the distortion introduced by the heating of the Earth's atmosphere, heating and mixing. So here, after the light, telescope collects the light, this light is sent to something called deformable mirror. A mirror whose shape you can manipulate. You can change its shape. So this is the wavefront. 3 wavefronts are shown. It's like all twisted and distorted. Now this deformable mirror will take a shape which is conjugate to this, which is opposite to the wavefront, which means you will be able to correct it. Okay? So somehow all you have to do is just measure how the distortion is happening, and if you can measure that distortion, you can command your deformable mirror to change its shape in such a way that a distorted wavefront becomes a flat wavefront again. And if the wavefront is flat, your image quality is restored. It's back to the diffraction limited image quality that the telescope can give. This is how the AO system works. So those who are interested in astronomy, it's not just observing stars and all, but it's also about developing this kind of technology to make your observations better. And if your observations are better, you can only then find new things. Okay, so building telescopes, doing instrumentations is also part of astronomy research. So some of you who want to become engineer, they also have a place in astronomy, right? Because engineers are the one who build instruments, they build telescopes, they understand these things better. Scientists basically are interested more in collecting light and analyzing what is happening on the stars, right? But to make that happen, to address challenging scientific questions about the universe, you have to build better and better telescopes and better instruments, and adaptive optics is also one of those challenging tasks. Is that okay? Very nice. Okay, so I'm just telling you, this is how the deformable mirror would work. You have deformable mirror is a mirror with reflecting surface, but that surface can be reshaped by putting actuator underneath it. All right? Okay. So this is the example how actually adaptive optics works. This is on a Gemini telescope. So light is collected by the primary mirror. There is a laser that's called sodium laser, 589 nanometer. That laser is pointed in the sky, it goes up to 100 kilometers, and it excites the sodium atom there, so they glow and emit light, and telescope is able to collect that light, and that light becomes your reference for sensing the wavefront. Okay, so let's see how it happens. So you are looking through the dome clearly. This is the laser which is shot into the sky. You're shooting the laser to the sky, and it goes to 100 kilometer height, somewhere where the sodium layer is. This is one way of doing AO. You can do it multiple ways. And here, where the sodium atoms are, because the wavelength of the light matches with those, the sodium atoms get excited, they emit light again, and that light which these sodium atoms emit backward is again collected by the telescope. Because you are sampling the entire atmosphere now, using this method, you can tell what aberrations are happening to the light. Okay, so you can do the sensing of the wavefront of the light, where it is twisted, where it is turned, where it is tip and tilt is happening. All those things once you have, you command your deformable mirror to compensate that, and that's what this is doing. So this is the light which comes back. It's a little slow, but that's fine. So when the AO is not on, watch carefully. This is how one can represent visually the optical light. So some part of the light is taken. So this is a star. As I said, because of the turbulence, you will not get a sharp or stable image. Okay, so the wavefront, these chip, the flakes-like things, they are all they are distorted. They don't have a flat shape. And if they don't have a flat shape, which means your image is not going to be sharp. But then some light you take and correct, and this is your deformable mirror. It exactly takes the shape which is opposite to the incoming wavefront and flattens it. So now the light is corrected, aberrations are corrected, and when you do that, this image will become more stable and much sharper. Correct? This is how adaptive optics works, and you need it for larger telescope. Otherwise, there's no point in building larger telescopes. Okay. That is enough. Now let's go to the main topic of today's thing. This is not very long. I'll just, because most of the basics I have covered, these are all just details. So next generation large telescopes. So far till today, the biggest telescopes that we have is around 10-meter class telescope. Okay, there are several of those 8 to 10-meter class telescopes, 5 or 6, but bigger than that still don't exist. And these are the 3 next generation large telescope, which is called ELT, Extremely Large Telescope. It is being built by ISO, European Southern Observatory, basically all the European countries together. And this is around 40-meter class telescope. Its diameter of this mirror is 40 meter. Then there is TMT, 30-meter class telescope, which is again, India is partner in this. I'm coming to the details of this. And there's another 20-meter, GMT, 24-meter class telescopes, which is again another group of scientists who are building it. So you have to remember a couple of things, that the largest size, a single mirror size that you can build with the current technology is roughly around 8 meters. You cannot make a mirror bigger than 8-meter size. So what happens if you want to build a 40-meter class telescope and you cannot make a mirror bigger than 8 or 10-meter class? Then first of all, why we can't make? What prevents it? Why? Yes, it becomes bigger and bigger. And bigger means its mass will? So there are several technological challenges to make a big mirror. One is that its mass will increase, and by its own mass, it will sag. Its surface will distort, and you cannot get a good telescope. Remember, all these things can only be achievable if the surface of either the lens or the mirror, they have to be very, very accurate. Less than 1/10 of the lambda that you are operating. I don't know if you are familiar with that, but let us say hair is 100 micron thick, typically, human hair, right? So the errors on the mirror surface should be less than 1,000th of the thickness of the hair. Better than that. Got some feel for that? Okay, think about it. So one thing is you cannot make big mirror because they will sag by their own weight and distort. So then what do? How do you go about building bigger telescopes? So only way to do that is build segments. Make many small mirrors, put them together and give them an overall shape of the mirror. Right? That can be done. That sounds doable, right? So what you see here, these are all segmented mirrors. All the big telescopes are based on segmented mirror technology. So this telescope has almost like 798 segment. Each segment is 1.5 meter, 1.4 meter or so. 1.4 meter is easy to build. So you build 700 of them, hex shape, put them together. Why do you think hex shape is better? Why we have not made circular mirrors? Yes, very nice. When you have hex mirror, you are minimizing the gaps, right? So collecting area is max. But if you put circular mirror together, there are going to be lots of gaps, right? You will not fill that pattern completely. Okay, so your ELT has 798 segments, which is a huge number. TMT has 655 and GMT has how many? 7, right? They are big. Each one is 8 meter and you can't make bigger than this. So they decided, okay, we will make 8 meter mirrors and put them together. Okay, all of these projects took different ways of building bigger telescopes. Okay. And ELT is the biggest telescope, and it's also like there's no problem with them. They are able to secure a site and construction is going on. And by this year, 2028, this telescope will be ready for observations, for scientific observations. TMT has some issues with the site. They are not able to secure the site as yet. So if TMT comes, it is going to be sometime after 2030, maybe mid-2030 or late 2030. And GMT also, a lot of progress has been made. Their mirrors are almost ready. So this will also start observing sometime early 2030. Okay, any other question about it? And they are also located in different places. ELT and GMT are located in the southern hemisphere, whereas TMT is going to be in Hawaii. And these are all dry places which provide dark skies, and also less of turbulence. Okay, so this is next generation large telescope, extremely large telescope. This is how it looks, the current status. They have already built the dome, and very soon they will start populating the mirrors. They'll start putting the mirror segment together. Okay, so these are the details. I don't want to really spend more time on this. But remember, this is going to be, the height of the enclosure is going to be 85 meters. I don't think we have any structure in Bangalore which is that massive. Okay, so remember, these are very, very massive telescopes. Okay, and as a result, the challenge of building the instrument as well as operating them is equally daunting. This is about TMT, 30-meter class telescope. This is the artistic impression of the telescope. And as I said, India is partner in this telescope. There are US, Japan, and China and Canada. So 4, 5, 6 partners are building it together. And as the operation is contingent to when the site is secured. This is that 7-mirror telescope called GMT, Giant Magellan Telescope, and it's going to be in trial and so on. Remember, each of these telescopes also have instrument planned. So telescope without the instrument is no use. You can't use it just to view things. You cannot, first of all, view objects with this. This is meant for scientific research. So all the telescopes also have first light instruments. Like this is a infrared imager. So Mikado, Harmony, Metis, Maury, these are all first light instrument, meaning when the telescope is ready, these instruments would also be there for making scientific observations. Okay. Some of them are imager, which will just take the images of the sky. Some of them are much more complicated instrument, which would also do spectroscopy. Spectroscopy is analyzing the light, what content is there in that, in terms of chemical components or chemical elements in the stars and so on. So, okay. Likewise, for 30-meter class telescope, there are 3 instruments which are planned for the first light. One is the infrared imager and spectrograph. There is a wide field optical spectrograph called WFOSC, and MODIS. This is a high resolution spectrograph. Each of these instruments would do different kind of science. Right? So many astronomers are working, each one is working in their own area, and they need a range of instruments, a suite of instruments which can help them do their science. So, any questions so far? Okay, fine. This is 30-meter telescope, another view of it. All these segments are put together. All right. This is a cut, dome cut of the 30-meter class telescope. So this is the primary mirror, and what you see on the sides is where the instruments are placed. These are called Nesmith platform. Okay, so I'll show you. So this primary mirror collects most of the light. Primary mirror and secondary mirror are definitely going to be there in every telescope. So primary mirror, this is secondary mirror. So light reflected from this goes here and then comes back to this tertiary mirror, which is flat. And this tertiary mirror is steerable. It can direct the light to any of these instruments which are placed on the outer periphery of the telescope. I'll show you that. So this is how, again, this is graphics illustration. I'll show you how. So this is the light coming from the star, hitting the primary mirror, going to the secondary mirror. Is becoming more and more brighter and more brighter because the area is reducing. And this is the tertiary mirror, which is at this angle, it deflects the light to this instrument. Then you change the direction of the tertiary mirror and direct the light to the another instrument. Further, if you change it more, it will direct to the third instrument and so on. So this is how exactly it would operate. Yeah? Yes, any question? Yes. So tertiary mirror is in the beam path. Even the secondary mirror is in beam path. That is true with all the telescopes, right? So your fill factor is not 100%, right? They also block some of the lights. That always happen. Yes?
Why
Why?
does GMT have circular? Why does GMT have circular?
Why? So 8 meter class mirrors, you can't really cut the segments to hex. Okay, you can do it. The segment that are used in the TMT and ELT, they are 1.4 meter diagonal. They are hex cut, right? And only 5 centimeter, 4.5 centimeter thick. So it's easy to shape them. Whereas the mirrors that are used for the GMT, they are several tens. Each of those are like 8 meter diameter and probably more than half meter thick. So you can't really make them into a hex cut easily. And they are also, they're not flat mirrors, they are spherical shaped. Okay, so technologically that is difficult. That's why you see the gaps there. All right, so this is about how the light path would look inside TMT. And okay, we have seen it. And okay, this is just to tell you that how big the TMT is. 30 meter diameter is almost of the size of basketball court. That is very, very big. And TMT is going to be 66 meter tall, the dome and other things, which is like 20-story building. And it can detect lights from objects which are billions of light year away. What does that mean? Billions of light year away means light coming from objects when the earth itself was not formed. Can you grasp that? Right? So you're going back in time. Yeah, it took that much time for the light to travel. So you're going not in terms of distance, but you are also going back in terms of time. Okay? And so that's true with all the 3 telescopes. Now TMT is so sensitive that it can detect the glow of candle on the moon. Candle, how much light it has. You put a candle here, you wouldn't be able to see the light from it if you go to half kilometer, right? But the TMT can do so. Even the candle is placed on the moon. Okay. Now, if your eye was like a TMT as big as 30 meter dia, then the TMT would be able to spot a firefly on Pluto. Okay. So this is just to give you some idea about the sensitivity and the power of 30 meter class telescope. I'm almost done. So as I said, all these telescopes will have adaptive optics because they will not function without the adaptive optics because you will not get the clear, sharp images. So this is, for example, this is the Io moon. This is Jupiter's moon, this is how it will look with a 10 meter class telescope. And this is how the TMT larger size, more details, that's how it's going to look. So you can see the volcanic spots on the this particular moon. This is again how the images would look from TMT. This is with one kind of AO and this is with another kind of AO, but you can see clearly the difference. If there was no AO, all these things would be lost. All the details would be lost. All right, so this is challenges of making large telescope. The biggest challenge is mirror fabrication, right? First of all, you should be able to remember big telescope means big mirror, and when you're putting segment together, all those segments should align to make the part of that big large mirror. And if there are small differences, it will not work, right? So big challenge is segment alignment and polishing. So here I am showing you, if these are the segment, each segment should form its own image and all the images should be at one place. Then only it will be part of the big mirror. If that doesn't happen, then your telescope resolution is not going to be what you aim to achieve. Okay, so see here, this is what is shown here. When the segments are not aligned, each one has its own image. So when you start aligning them properly, now question is to what degree of accuracy you have to align them. Again, it has to be aligned better than nanometer kind of accuracy. Then only you will get the diffraction limited image from the telescope. So diffraction limited image is just a phrase used to tell The telescope is giving you the best that it can, right? But if this alignment, segment alignment doesn't happen, if the atmosphere aberrations are there, you will never get that diffraction limited performance from the telescope. Okay, so adaptive optics has to be there. Your site selection also has to be proper to really exploit the best science from the telescope that it can give. Of course, there are other things like cooling and thermal control that has to be done better. Instruments are going to be really, really complex. You can see here, there's a small person standing here, and it's really huge. Each instrument is going to be like this, a room of this big or even bigger, right? So that's a challenging thing. This is transporting the 8-meter class mirror for GMT. Now, mirrors are made somewhere. They have to be transported to on a hilltop, and that's not going to be easy. Sometimes you have to make roads, you have to get permission, make bridges. So there's a lot of stuff involved. Of course, more important is the cost. These are very, very expensive projects. No single institute can do it, so people have to collaborate. Institute have to collaborate, countries have to collaborate. Then only you'll be able to meet the scientific requirements. So I think with that, I would stop. India is also partner of TMT project. So we are, for example, making out of 492 segments in TMT, India is going to build around 80 segments, and that facility is already operating in a place called Crest here, 40 kilometers from here. So this is India TMT optical facility where these segments are built. First you have a circular segment, then you cut into a hex shape. So that's all will be done. We are also making segment support assembly, very complicated structure which will hold the segment properly, because that alignment segment has to be aligned to the accuracy of few nanometer. So all these things are required to give you that best image that telescope can produce. Okay, so I'm done with that, and it's a question time if you have any. Yes. Huh? Focal ratio of GMT is slightly less than 1. TMT has 1, and even the ELT has, slightly less than 1. Now, focal ratio is made less because if you increase the focal ratio, the size of the telescope has to be increased. Now, already we are talking about 80 meters. Okay, so structure that's holding the primary mirror, secondary mirror, and the tertiary mirror, that will become bigger and more complex. So that's why the focal ratio is kept small for the telescope. See, focal ratio can be manipulated later within the instrument, so that's not a problem. I didn't talk about focal ratio, but that's an important quantity or parameter of the telescope. Yes, please. Yes. So just liquid mirror, I think so, as long as you can really reshape them with a very high speed. See, the turbulence, the turbulence induced by Earth changes at millisecond time scale. So if you can reshape them like 1,000 times per second, yeah, liquid mirror should also be working fine. Yeah.
But liquid mirrors, if I'm not wrong, comes with its own challenges of degree of viewing in the sky.
I don't know, so I'm not aware of liquid mirrors. Yeah. No, these mirrors don't have to look to the sky. They are all post focal plane. So they are put in the instrument room or somewhere, right? Currently, these deformable mirrors are made with like piezoelectric actuators, which are basically driven electrically and reshape the mirror. Yeah. So you are going to be involved in a very important exercise of assembling these telescopes. To reach there, you have to understand this, what you're going to do today. Okay? So apply your heart and mind and try to understand. Ask questions from your people who are going to teach you this, right? Because everything else is just scaling things. If you understand why you are doing what you are doing, they're not going to grind and pulse and make lenses. So that somebody has already done. So you will be given a lens which is of decent quality, right? Quality in terms of how smooth the surface is, right? Whether it is, or reflector, even better. Okay, so the refractor quality is already, people who have built them, they have ensured that they meet the desired quality. And that's a challenging thing. Read about it, how it is done, how the mirrors are polished, how they are given the desired shape and all, right? Because it's like it has taken several decades of work for people to perfect such technologies. Okay, so yes, any more question, please?
I think I have a question to the students.
Yes.
After going to the talk, I would like to know what size telescope would you like to build? You all know that you are making 5-inch one.
Yeah.
But what would you desire?
Ultimately.
The largest one. 40 meter. Oh my God.
Yes,
You know
yes.
how expensive it would be, and where are you going to put it up? That's what I was talking about. Where are you going to put it? On your roof.
Yeah.
Yes, ma'am, 1 meter.
But remember, whatever you are going to build, you start small. And that's today is that day. Okay? So pay attention to the details, see what it is doing, understand it, and then rest all is just scaling your ambitions to make bigger telescopes. Ask question and read more. That's a way to go forward. So if not, then thank you very much for the patient hearing and asking a lot of questions and also answering them. Okay. All right.